All right, problem number 5. We have a rectangle ABCD and it's made up entirely of squares. The small black square has a side length of 1 unit, and we're asked to find the area of ABCD in square units. All right, well, this isn't too hard. Let's just we're given that this little black rectangle is 1 square unit, right? So I'm just gonna, if it's 1 square unit, then the side length here has to be 1, right? Oops. And since it's adjacent to this other little square right here, that one also has to be 1 unit, right? So we have these two 1 square unit squares here. So this side has to be 1 over here. I'll just mark that in there. And it's adjacent, these two squares are adjacent to this square, so 1 plus 1 is 2, so this square has to have a side length of 2, right? And I could put a 2 over here, I could put a 2 over here, and a 1 here, and you can see that 1 plus 2 is 3, so this has a side length of 3. Okay? And we could put a 3 down here. Alright, and now this square is adjacent to this 2 by 2 square and a 3 by 3 square. So this has a side length of 5. I could write 5 here. Oops. I could write 5 here. Okay. And now this square here with the B at the corner is adjacent to a 5 by 5 and a 3 by 3. So this one has to have a side length of 8. And I'll put an 8 there, 8 there, and an 8 there. Okay, so that's an 8 by 8. And now this square down here with D at the corner, it's adjacent to this 8 by 8, a 3 by 3, and a couple of 1 by 1s. So that's 11, 12, 13. So this one has to have a side of 13. Alright, I can write 13 down here, 13 here, okay. And now we just have one more square to figure out. And it has to have, it's adjacent to this 5 by 5, a 2 by 2, a 1 by 1, and a 13 by 13. So if we add up all of those side lengths, we get, let's see, 1 plus 2 is 3, plus 5 is 8, plus 13 is 21. So this is a 21 by 21 square. Alright? We're asked to find the area, so if we know the dimensions, we can just multiply them times each other. So it looks like the height here of this rectangle is 21, and the length here is 21 plus 13, which is 34. So let's just take 34 times 21, and we'll get 34 and 68. So we get 714 square units. Alright? And that's the answer. Okay? That's one way to do it. The other way to do it would be to look at all the squares and you could figure out their areas. So you have a 1, the area here would be 4, the area here would be 25. Here's a 64. 13 by 13, that's 169. And 21 by 21, what is that? 21 by 21, I can't figure that up in my head. 21 and 42, so what is that? 441, okay? 441. And if you add all these up, 441, 169, 64, 25, 4. Oops, I didn't mark this one. This is a 3 by 3, so this is 9. And then a couple of 1s, you'll get the same thing. You'll get 714. Alright? So, let's take a little closer look at this rectangle too. Since that went pretty fast, I wanted to, this rectangle is kind of a special rectangle. Don't you think it's beautiful? It's often called the golden rectangle, or it's an approximation of the golden rectangle. And you might recognize this series of squares, okay? We have two 1 by 1 squares right beside each other, right? And then we have a 2 by 2, we have a 3 by 3, we have a 5 by 5, we have an 8 by 8, we have a 13 by 13, and we have a 21 by 21. And some of you may recognize this series of numbers. This is the Fibonacci series. Okay? And the Fibonacci series is just created by the first two numbers, you add them together, and you get the third number. And then you take those two numbers, and you get the next number. So you're just taking each adjacent number and getting the next number, right? 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and you can see that the next number in the list would be what? It would be 34. So we could actually add another, if we were to take another rectangle and add it on down here, 34 by 34 rectangle, we could do that, right? But this is the Fibonacci series, and it has some special properties. I won't go into them right now because I'm, don't have a whole lot of time. But I'm going to erase some of these. This series can actually be used to approximate the golden rectangle. The golden rectangle is, at least the Greeks called it the golden rectangle, is the most beautiful rectangle. And architects, Greek architects used it as the basis for like the Parthenon, and so they considered this to be the most beautiful rectangle. That its shape was, you can imagine that flags are sort of this shape, and so let's look at this here. If I look at the ratio here of 1 to 1, actually, you know what, it'd probably be easier if I write this Fibonacci series this way. So we have 1 and 1, and their ratio is just 1, right? The next number in the Fibonacci series would be 2, and the ratio, if I take this this number over this, 2 over 1 is just 2, right? Next would be 3, and if I take 3 over 2, I get 1.5, right? And let's see, I'm going to scroll down. I run out of room here. If I take the next number, which is 5, and I look at the ratio here, 5 over 3, that's just 1 2/3, which is 1.666, repeating 1.67 if I round it off. Okay? And let's take a look at the next one. The next number would be 8, and if I take this ratio, 8 over 5, I get 1.625, right? And the next number would be 13. If I look at that ratio, 13 over 8 in decimal form is 1.61538. Now I rounded that off, but that's a decimal point. And I did this on the calculator before, and I'm not able to do this in my head. Okay, next number is 21, and 21 over 13. If I plug it into a calculator and get it in decimal form, I get 1.61905. And I'm just, for the heck of it, I'm going to go ahead and do 34. If I take 34 over 21, I get 1 point, hang on a second, I think I'm off here somewhere. I think let's see. Oh, you know what? I am off. This is supposed to be, this is actually 1.6, alright, and this belongs here, okay. I'm going off of my, I'm going off of my notes here, so anyway, yeah, 8 over 5 is 1.6, 13 over 8 is 1.625, so they're just, they're off a little bit. But the thing I wanted to show you is that if you were to keep going with the Fibonacci series and take ratios of adjacent numbers, you approach a number that, you know, doesn't look all that special if you put it in decimals. 1.618 034. But this number, and this is actually just an approximation, it actually has a lot more. It's actually an irrational number, okay? An irrational number is just one that can't be expressed as a ratio of two numbers, okay? So like pi is an irrational number. The square root of 2 is an irrational number, okay? It has these numbers after the decimal point that go on forever, and they never repeat, okay? And this number is called phi. It's a Greek letter, phi. And the Greeks called this the golden ratio, okay? And hence you can not ration. You can kind of guess why they would call this the golden rectangle, because as you add more and more of these squares to this rectangle, then the ratio of the sides approaches this number called phi. So that's kind of a, you know, quick introduction to the golden ratio. But if you want to read more about it, it's kind of an interesting topic to look into. You know, if you type into Google golden ratio or golden rectangle, you'll find all kinds of information on these things. So just giving you a little taste.